Hi everyone, this is lesson 1.7, and in this lesson we're going to talk about combining functions or the combinations of functions. The learning target for this video will be that I can perform operations on functions. In lesson 7, like I said, we are going to be talking about combinations of functions. Two functions can be combined to create new functions. Let f and g be two functions with overlapping domains. That means their domains intersect, that they share some values that are the same in both of their domains. Then the algebraic combinations of f and g are defined for all x values common to both of the domains. So think about a Venn diagram here, right? If we have function f and function g, and we are talking about their domains, the values they have in common are where the two circles intersect. Now, the sum function, there's four different operations we're going to discuss. The sum function, f plus g of x, is really just f of x plus g of x. So if you see here, what's written is f plus g of x, because both functions have an independent variable of x, you can separate that out and say f of x plus g of x. The difference function, f minus g of x, because again, f and g both have an independent variable of x, you can rewrite that as f of x minus g of x. The same thing can be done with the product and the quotient. We have f times g of x. Again, since f and g both have independent variables of x, you would have f of x times g of x. And then the quotient, f divided by g of x, would be f of x divided by g of x, as long as g of x is not equal to 0. Remember, g of x would not equal 0 because we are unable to divide by 0. The note on the domain here says, in each case, the domain of the new function consists of all numbers that belong to both the domain of f and g. The zeros of the denominator are excluded from the domain of the quotient. So again, they're just referring to the fact that any x values that would make you or cause you to divide by 0, so where g of x is equal to 0, are excluded from the domain. So again, the domain of the new function consists of all numbers, all x values, that belong to both the domain of f and the domain of g. In example 1, we are going to look at two functions. F of x is equal to 5x minus 8, and g of x is equal to 7 minus 2x squared. In letter A, it says find f minus g of x. So really what they're saying, f minus g of x, the difference is f of x minus g of x. Now, when I substitute f for f of x, when I replace f of x with the actual equation, right here, I am going to use grouping symbols. So I have 5x minus 8, that's my function f, and then I'm going to subtract from that function g, which function g is 7 minus 2x squared. So when I replace g with 7 minus 2x squared, again, I will use brackets or grouping symbols there. And when I simplify now, when I do actually calculate the difference, this subtraction sign in front of g is really like a minus sign or an opposite sign that needs to be distributed to the entire function. So I have 5x minus 8, and if I distribute, I get minus 7 plus 2x squared, right? I'm going to distribute the minus sign. I get minus 7 plus 2x squared. So I actually get 2x squared plus 5x, right? The 2x squared goes first because it has the highest exponent, 5x, and then a negative 8 minus 7 is negative 15. Now, in the next difference, we have f minus g of 4. Well, here we don't have an x variable, but we have a numerical value. So what that means, f minus g of 4, means to take f evaluated at 4 and subtract function g evaluated at 4. Now, if I evaluate f of 4 is 5 times 4 minus 8, or that would give me 20 minus 8, which is 12. 5 times 4 is 20. 20 minus 8 is 12. G of 4 is 7 minus 2 times 4 squared. Again, I'm going to plug in 4 for x in the function g. And I get 7 minus 2 times 16. 4 squared is 16. Or 7 minus 32, which is negative 25. So f of 4 minus g of 4 really boils down to, since f of 4 is 12, minus g of 4, g evaluated at 4 is negative 25. I actually get 12 minus a negative 25, which is 12 plus 25, which is 37. So that would be our final answer, 37. Now, another way you could approach this, and this does not always work, but if you've already calculated f minus g, if you've already done f of x minus g of x, right? F of x minus g of x. We already have that function right here from part A. Then really, if I want to take f minus g evaluated at 4, I could take the answer I got from A right here, this function, and I could have just said 2 times 4 squared, right? 2 times 4 squared was here, plus 5 times 4 minus 15. Now if I simplify this, I get 2 times 16 plus 20 minus 15, or 32. 32 plus 5. 20 minus 15 is 5. 32 plus 5 is still 37. So this new method that I used only works if you've already calculated the difference of f and g. Since part A asks us to calculate f of x minus g of x, or f minus g, since I already had that calculated, I could just plug 4 straight into that function and get 37. The same way I broke it up originally by taking f of 4 minus g of 4. Now, in example 2, it says let f of x equal x cubed and g of x equal square root of x plus 1. Find the following, give the domain for each. So for f plus g, the operation would be x to the third plus square root of x plus 1. F, the function f up here, is x cubed, and g of x is square root of x plus 1. I don't have any like terms that I can combine here. X cubed cannot be combined with radical or square root of x plus 1. Now if you look at that function, the domain for f is all real numbers. If I graph x cubed is a polynomial. the graph of the function for f would be something like this. It goes from left to right infinitely. G of x is the square root of x plus 1, and if I graph g of x, that is a shift of the square root function left 1 unit. And if we shift that to the left 1 unit, it looks something like this, which means the domain for g is from -1 to infinity. Now, when you calculate the domain for this function, it is going to be where those two domains intersect or overlap, right? If we go back to the definition up here, it said that the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g. So if I think about that, f is all real numbers. G is from -1 to infinity. So on a number line, this is what it's going to look like. For G, I'm going to shade from -1 to infinity. And for F, I would shade the entire line. So if you look at where the overlap is, the functions overlap from -1 to infinity, right? Where I shaded in both blue and in red is from -1 to infinity. I just highlighted that in yellow. So we can say the domain for f plus g, the domain, would be from -1 to positive infinity. Now, for the difference, we would take x cubed minus square root of x plus 1. Again, I cannot simplify those two functions. There's no like terms. I cannot combine an x cubed with a square root of x plus 1. Again, f and g, the individual functions, have the exact same domains. F is still x cubed. G is still square root of x plus 1. So their domains remain unchanged. And therefore, f minus g is still the overlap of the two individual functions. So the domain of f minus g is still going to be where the two individual domains overlap, which is again from -1 to infinity. For f times g, we get x cubed times the square root of x plus 1. I cannot multiply that x cubed. I can't distribute it into the radical or square root, so we just leave that alone. Again, the same thing that happened up here and here is that f, here's function f, and here's function g. F was in red, and g was in blue. And again, the individual functions still have the same domain, so the product of those two functions will have a domain from -1 to infinity, because the two individual functions have domains that overlap from -1 to infinity. So this is the domain for f times g. For f divided by g, I get x cubed divided by square root of x plus 1. And x cubed divided by square root of x plus 1. F is still -infinity to infinity. This time g, I'm going to do f in red here. F is still -infinity to infinity. But this time, the denominator here cannot equal 0. So here, if I look at the graph that I drew for square root of x plus 1, the function looks something like this, -1, and then 1 to the right infinitely. I cannot include -1 in the domain of the function of the quotient because negative 1 causes me to divide by 0, right? If I look at the function right here, if I substitute negative 1 in for x, I get negative 1 cubed divided by square root of negative 1 plus 1. That would give me negative 1 over the square root of 0. Square root of 0 is 0. Therefore, I get negative 1 divided by 0. That's undefined. So when I look at g, the blue function is still, the domain for g is negative 1 to infinity. However, when I divide f by g, I can no longer include negative 1 as part of my domain. So we'll say that the domain for f divided by g is actually from negative 1 not including negative 1 to infinity. Right? F divided by g can no longer include negative 1 because if we substitute negative 1 into that ratio or quotient, we end up dividing by 0.